Okay, so this is a video on some basic circuit theory in which we'll look at what voltage is, what current is, and what resistance is. So let's start with this basic circuit symbol for an electrical bulb, which when attached into a circuit will allow a current to flow through it. So what do we mean by an electrical current? Well, we define current as the rate of flow of charge. So this means that we have charged particles moving through the bulb. So this gives us an equation where we can say that the current is equal to the rate of flow of charge. So if we represent charge with the letter Q, and we say that there is a time taken for a certain amount of charge, which would be measured in coulombs, to flow through that bulb, that charge divided by the time taken is the current in amps. So if we have 1 coulomb of charge flowing through the circuit in 1 second, then we have a current of 1 amp flowing around our electrical circuit. Right, okay, so we've got a current. We also know that if we've got a current flowing through our device, then there'll be a voltage associated with this. So let's have a think about voltage. Now, we talk about voltage, there being a voltage across the component. So what does this mean? Well, if we have a voltage of 9 volts on this side of the bulb and a voltage of 6 volts on the other side of the bulb, that means we have a potential difference of 3 volts. And if we attached a voltmeter across our bulb, we would measure that 3 volts. So why is there a difference in voltage across our circuit component here? Well, this links into the idea of electrical energy. So the charge that's flowing through our bulb carries energy, and that energy is being transformed into heat and light by the bulb. So the charge that's flowing through at this point here, okay, has more energy than the charge at this point here. So some energy has been transformed into heat and light, and the change in voltage represents the fact that the charge that carries the energy has less energy when it leaves the bulb. So when we talk about volts, another way of expressing the volt is to express it as joules per coulomb. So that means that in this case, for every coulomb of charge that flows through that bulb, 3 joules of energy are being converted into heat and light. So it started as it flowed in, it was carrying 9 joules per coulomb. As it flows out, it's got 6 joules per coulomb. 3 joules per coulomb of charge is being transferred as the charge flows through that device. Okay, we've had a quick look at current and a quick look at voltage. So let's have a look at the relationship between them. So if we just move this over and we'll talk about a resistor. So when we think about current and voltage, we know that they are directly proportional to each other. So if I take a circuit component and I increase the voltage across it, I would expect the current to increase. So we can say that voltage is proportional to the current. As we know, we can then sort of find some sort of constant of proportionality to relate the two, and as you know, well, that leads us to the expression that V is equal to IR, where R is the resistance. So this means that we have a voltage across, a potential difference across our component, and a current flowing through it. The current is limited by the size of the resistance of the component. So a simplified way of looking at it is the more resistive a component is, the less current it allows, the more resistance to current it has. As we know that inside the actual material you've got a lattice of atoms vibrating away, getting in the way of the electrons as they try to move through. So the more that happens, if the temperature goes up, if there are impurities in the material, then the resistance will increase. So, as an example, if we had 3 volt supply across this resistor, okay, we would say that 3 is equal to whatever the current is times the resistance, and if the resistance was 50 ohms, okay, we would have 3 is equal to 50 times I. So we can rearrange that and say that therefore the current is equal to 3 divided by 50. So therefore the current in this case would be equal to 0.06 amps or 60 milliamps. Okay, so let's have a look at an actual circuit then and apply these simple theories to the circuit. So the first one we're going to look at is a series circuit. We've got 2 resistors which are in series with each other. So we can spot a series circuit because there is just one single loop. That means that for our circuit that the current I is the same everywhere. Okay, so we've got the same current there, we've got the same current there, and we have the same current there. This is because it's one single loop. There's nowhere else for the charge to go. So once it comes out of the battery terminal, it must flow around through the resistors and back because there is just one single path. For our circuit, the same equations apply as we had before, so we've still got V is equal to IR, and for this circuit the total resistance, okay, is going to be equal to R1 plus R2, if I can get that in there. So they just add together because as you add resistors in series, they're adding more resistance to the circuit, making it more difficult for the current to flow round, so the resistance gets larger. So let's take, for instance, 2 values here. If we say that we have an 18 ohm resistor there and a 12 ohm resistor there, we can also say that in this case, let's just say we've got a 9 volt battery. So our total resistance will therefore be RT is equal to 18 plus 12, which is equal to 30 ohms. Right, so the current, which we've already said is the same everywhere, is going to be linked into the voltage via V equals IR. So in this case we have a current. If we rearrange V equals IR, we can say we've got a current I is equal to V divided by R, so therefore that is 9 divided by 30, okay, which gives us a current in our circuit of 0.3 amps. Okay, so we can use that result, current is equal to 0.3 of an amp, to work out the voltage drop, the potential difference across each of the resistors, if we wish. So we can, if we just move that up slightly, we've got 18 ohms, so we can say that the potential difference V across the 18 ohm resistor is going to be equal to the current flowing through that resistor, which is the same value everywhere, so it's still the 0.3 amps, times the resistance of the 18 ohm resistor, which is obviously 18. So that gives us 0.3 times 18, which gives us a voltage drop potential difference of 5.4 volts. Sorry, 5.4 volts. So that means that 5.4 joules per coulomb of charge will be transferred into heat at that resistor. and as it's a potential difference of 5.4 volts, if we look back up at our circuit, we could then work out that, as we know that at this point here, we have a voltage of 9 volts, okay, because it's directly linked to the positive terminal of the battery. Then therefore there will be a drop to this point here of 5.4 volts. So the actual potential at the point in between the two resistors is at a voltage of 3.6 volts. Okay, and if you do the calculation yourself for the voltage drop across the 12 ohm resistor, you should see that that links in nicely, because at this point here we're looking at a voltage of 0 volts because it's connected to the negative terminal of our battery. Okay, let's have a look at one last circuit, and we'll have a look at this circuit here. So we're going to look at a parallel circuit this time. Okay, now for our parallel circuit, let's have a look at what the implications are for a voltage. Well, we've got both sides of the resistors are connected to that side of our battery terminal, so both the left hand side of each resistor is connected to the positive terminal, and both of the right hand sides of our resistors are connected to that side of the battery terminal. So we can see from this that both resistors have exactly the same voltage across them. So that's the first thing about parallel circuits. For these two resistors in parallel, they both have exactly the same voltage across them. Okay, so let's have a look at what the implications are for the current for this circuit. Well, if we look at it, we've got a current coming out of our cell. Okay, we'll call that the total current, and that flows to this junction here where it will split, and we have some of the current travelling down here, we'll call that I1, and we've got some of the current travelling down there, which we'll call I2. Alright, so what that means is that the current that's flowing into that junction, which we've got as the red dot there, must equal the current that flows out of that junction, because there's nowhere else for it to go. So we can say that for our parallel circuit here we have a total current which is going to be equal to I1 plus I2. Okay, so the current flowing into that junction is the same as the current flowing out of that junction. Right, let's give the components some values to illustrate this. So if we say that our EMF, our voltage source, is 12 volts, okay, and that our resistors, let's take this resistor here as 15 ohms, okay, so it's 15 ohms, and the resistance of this resistor here we're going to have, as 30 ohms. Alright, so that will allow us to work out some of these currents, because if you remember, as we said, the voltage is the same for each resistor, so each resistor has a voltage of 12 volts. We can use V equals IR, so we can rearrange that to get that I is equal to voltage divided by resistance. So I1 is going to be equal, I1 is going to be equal to the voltage, which is 12 volts, okay, divided by the resistance, which is 15, so that should give us 0.8, and then we can, by the same method, we can say that I2 is equal to, again, 12 volts, because we have the same voltage, divided by 30, which is equal to 0.4. So we now know I1 and I2. The combined values of each are equal to IT, so we can say that our total current for this circuit is going to be 1.2 amps. Right, that leaves us one thing to look at for this parallel circuit, which is the effect of combining two resistors in parallel. So if you look at this circuit, you can see that because we've got more pathways for the current to flow through, more current is flowing, which means that the combination of these two resistors gives us a lower resistance than each of the individual resistors on their own. So we can use the relationship that 1 over the total resistance is equal to 1 over each of the resistors that you have in the circuit. So in our case we've got 1 over R1 plus 1 over R2. If we had more resistors in parallel, we could just continue with that equation for however many resistors we have. So in this particular example, we have 1 over RT, the total resistance, the combined effect of those two resistors is equal to 1 over 15 plus 1 over 30. Alright, now if you work that out, you'll find that that comes to 1 over 10. So therefore, our total resistance of those two parallel resistors is equal to 10 ohms. So what that means then is, if we just go back to the circuit for a second and have a look at that, we have these two resistors, 15 ohms and 30 ohms. They combine to give us a total resistance of 10 ohms. And the last thing I'll let you do is for a resistor of 10 ohms and a voltage of 12 volts, you can work out the current that's flowing through that and compare that to the value for IT that we worked out earlier. Okay, and that's the end of this sort of summary of some of the basic circuit features.